We're happy to have Professor Eli Waxman from Weizmann Institute. Eli is a high-energy astrophysicist who is about to fly some satellite in 26 or something, and he will tell us about this satellite and why it is important on Thursday during the colloquium. And today he will be in his high-energy astrophysicist capacity, which I think is his strongest side, and he shouldn't fly satellites. He should be doing astrophysics, I think.
Thanks, Andre. I will fly the satellite anyway. Okay, so thanks for inviting me and for this introduction. And indeed, I'll talk about some high-energy astrophysics stuff. A few months ago, there was a detection of extended, strong near-infrared emission following a long gamma ray burst, and this initiated some excitement in for the high-energy types. Not most of you, but Andrew maybe. And so I'll try to explain why this is interesting, why it's maybe exciting, and what I think is the real explanation of this, rather than what maybe it's commonly discussed. Okay, so just a brief introduction. Slides. So just a very brief introduction to get everyone on the same page. Gamma ray bursts are short flashes of emitting photons mainly. They are divided into two duration classes. You can see this bimodal histogram here of durations, with long duration bursts lasting for like 20 seconds and short ones something like 0.2 seconds. Now I'll say a few words about the general characteristics. I mean, and the population is very diverse, and probably some is mixed and so on. So this is just a sort of very broad brush to get everyone familiar with these things. So the long duration GRBs, they are typically observed at a redshift of 1.5, 2. They are very energetic, 10 to the 53 ergs in gamma rays. The local rate is about 1 per cubic gigaparsec per year, and they are typically associated with relatively low mass and star-forming galaxies. The short duration GRBs, they are less energetic, 10 to the 51 ergs. They are mainly observed at low redshift, around half. The local rate is about 10 times higher, and they are typically associated with massive galaxies, with star formation, and one should know that many of them lack association with galaxies. Okay. Now,
But that's just an observational thing. You're not saying that they're not associated with galaxies.
No, they don't have association, observed associations. It could mean many different things. It could be high redshift. It could be large offset from a faint galaxy.
What's the difference between massive star-forming galaxies and low-mass star-forming galaxies?
So these are these are low mass and these are high mass galaxies.
Right, but from the point of view of stellar population, are they supposed to be different?
And the other thing is that these low mass galaxies have a star formation rate, specific star formation rate, which is significantly higher than these.
Oh, in fact, it is higher.
Yes. The specific is much higher.
They have a typically different metallicity.
Yes. Yes. So this may say many things about the progenitors, which is the next point I just want to go briefly over. I will not go into details in any of this because this is sort of just an introduction. Okay, so the long duration GRBs are commonly accepted to be produced by core collapse of strict envelope massive stars, type 1BC supernova. Now, what is this based on observationally? So there are many GRBs which are associated with such supernovae, but most of them are low redshift GRBs, low energy, 5 orders of magnitude lower energy than the typical cosmological GRB. And they are indeed associated with this 1BC supernova, and the rate is much higher than the cosmological GRB rate. So this is a solid association, but it's not the cosmological population. Now there's a handful of events which are sort of transition events, which are higher luminosity events, like 10 to the 52 ergs, and they are indeed associated with different types of supernovas. So there's a few of these. And there's also a handful with very stringent upper limits on an association with a supernova. So 100 times fainter than those 1BCs. So this is what we know. So probably some of the cosmological GRBs are related to core collapse of strict massive stars, but most likely there are other progenitors as well, which are not these supernovae. Now, the short duration GRBs are commonly believed to be associated with neutron star mergers. What is this based on? Observationally, not much. So we have one association of single binary neutron star merger that has been observed, 17 or 817. It had a gamma ray flash, but this flash again is many orders of magnitude weaker than the typical GRBs. But okay, this is some suggestion. And there have been several claims for the detection of a kilonova foreign short GRBs. What is a kilonova? In a neutron star merger, there's a highly neutron enriched mass ejected, and this leads to the formation of very heavy isotopes, which decay and heat up the envelope like a supernova, but these heavy isotopes have high opacity, so the emission is much redder than the regular supernova. And in 17 well, we've seen some red emission days after the burst, and there are some claims that in some short GRBs, some days after the explosion, you see such red emission. But I should say that these are, if you look at the data, it's far from convincing, I would say.
On the last point about the long GRBs, it seems very hard to put a stringent upper limit on the absence of a supernova association, because if you just had the GRB, correct me, if you just had a GRB in isolation, it doesn't have spectral features, and so you'd have to do it because you thought.
If you have a supernova, you see it, unless.
Yeah. But to say there's an upper limit on the absence of supernovae.
No
Sorry, maybe too many double negatives.
There's an upper limit on the presence of a supernova.
Yeah, that's what I thought you were saying. Okay.
The presence of a supernova.
But it seems to me very hard to prove that, because unless you know the distance, and it seems like isolated. How would you know the
So you locate the GRB with the X-rays. There are excellent localizations with X-rays. So
you say geometrically, you say if it's lined up with the galaxy, I'm going to assume it's from that galaxy.
So the chance probabilities are usually very, very low, and we see the afterglow. So we see the X-rays, we see the afterglow.
But the afterglow doesn't prove it's the association.
No, but it's consistent with the galaxy. Wait, so the main thing that could go wrong is large extinction that would suppress the supernova. But because they do have good afterglow observations, we have upper limits on the extinction too, and we see the galaxy, so we also know that it's not heavily extinct.
If you were right in associating with the galaxy, I
but the
agree.
chance probability.
If you had enough examples, maybe you could.
No, even if a single one, the chance probability is very small.
What's the angular precision?
It's about seconds
for the localization of the. That's small.
That's small. So I think it's quite safe.
But if it's not a supernova, then what?
So
what instrument gives you subarc-second localization in the X-ray?
Soft X-ray. It's not 10 keV.
It's like arc second, right? An X-ray.
Well, this is the PSF, and if you have high enough flux, Yes.
Yeah, so the PSF is in sub-arcsecond for sure.
So okay, this is one of the, so there are open questions about the progenitors, which is why this is sort of all interesting. And this is the context of the detection of this near infrared emission. So I'll say a few words maybe about what the progenitors are, but let's go to this near infrared emission and why it is important. Okay, before going to the near infrared emission, just to put everyone on the, again, on the same page about the commonly accepted models for the GRB. Okay, so this is the cartoon, which is, this is the widely accepted picture. We believe that these events are produced by mass accretion onto a compact object, which leads to the generation of highly collimated, highly relativistic outflow with Lorentz factor of about 100. We believe that some internal dissipation mechanism within this outflow, the distance of about 10 to the 13 to the 10 to 15 centimeters, leads to the generation of the gamma rays. And later on, this plasma collides with whatever material is around the exploding object, and it drives a shock wave into the surrounding medium, which produces the X-ray and radio and optical afterglow that we see for months after the emission of the gamma rays. Okay. And there is some transition phase where this ejecta is being decelerated by the material that it hits. There's a shock wave that goes back and decelerates the ejecta, and this also produces radiation that we expect to be in the optical illumination. Okay. Now, there are many open questions. The physics of this is far from fully understood, but I think that we have strong observational support, which I will not go into, for several facts. First, that we do have a highly relativistic collimated outflow. And second, that the afterglow emission, this radio to X-ray emission lasting for days to months, is produced by a shock wave, a collisional shock wave that goes into the interstellar medium and accelerate electrons by sort of Fermi shock acceleration, which then radiate synchrotron emission that we see as the afterglow. So these things are, I believe, are fairly solid. Okay, now we have all the background. We go to this near infrared thing. So this GRB was observed in X-rays, UV, optical, and infrared wavebands, and it was a long GRB, tens of seconds long, and it had an afterglow, which you see here. And the unique thing about this afterglow was that after a few days here, there was very strong near-infrared emission. This is about 1 micron here, which is well above what you expect from the typical afterglow. And the ratio of the, say, 2 micron to 1 micron fluxes was about 30. So it's a huge ratio. This cannot be explained by synchrotron emission, and also it cannot be explained by any normal supernova or abnormal supernova that we know.
Is it consistent with thermal?
Yes, I would throw it.
Okay.
That's what I think. Now, so what could be the source of this red emission? So I mentioned that in the Neutron Star merger, we expect the ejection of highly neutron-rich material that produces heavy isotopes that have high opacity, and they are radioactively heated, and they produce red thermal emission. So immediately several papers saying, okay, this is a kilonova, this ejecta from Neutron Star merger, which implies that this very long gamma ray burst was produced by merger of neutron stars, which typically they are believed to produce short gamma ray bursts.
Can you please rigorously define a kilonova?
Rigorously, I cannot, no. But roughly, I know it's the. Okay.
Is it a weak supernova?
A kilonova is a very red weak supernova and very fast. So the material that is ejected from a neutron star merger is low mass, a few percent solar mass, and very high velocity, 0.2, 0.3 c. So the evolution of the light curve of a kilonova would be on a day time scale, rather than months time
Is it a
scale.
theoretical or observational object, kilonova?
So it is, there is one observation, 17/817, and it's sort of consistent with what I was saying. Well, maybe not with the colors, but roughly it's consistent with having a few percent solar mass ejected at 0.3 C, radioactively heated, and with strong infrared emission after several days.
What is the redshift?
That's a good question. So these guys associated this, they claim an association with a very low, relatively low redshift galaxy. And I would say a few words about this, because I'll talk about this issue of association with the galaxy in this case. Okay. So if this is true, this is sort of arguing that maybe many of the long duration GRBs are produced by neutron star mergers, which is completely different than what we thought. And it would change the rate of neutron star mergers if the long GRBs are produced by them and so on. And it's going to be very interesting if this is really a kilonova.
This is back to this non-supernova origin of long GRBs.
Right.
Okay.
Yes.
You have some of them are kilonovas.
Yes.
Okay.
Okay, so I want to suggest an alternative explanation. This is actually something that we predicted a long time ago, and I'll explain this in some detail. So we argued that long bright GRBs should occasionally be followed by bright 10 to the 52 Hz per second thermal 1-2 micron emission lasting for like 10 to 20 days. Okay. So, and this is due to dust heating and sublimation, nothing to do with kilonova. So I'll try to explain what this dust sublimation is, what the physics of it is, and why I think what we saw in this case maybe is one example of such dust emission. So, so this is the idea, this is the scenario that we are discussing. Okay, so we are thinking of a relativistically expanding collimated jet, and we are considering this the stage where the expanding plasma just begins to be decelerated by the surrounding CSM. And so we have a forward shock going forward into the CSM, and we have a backward shock going into the jet plasma decelerating. Now, this forward shock emits X-rays, other X-rays. The reverse shock would typically emit in the UV. Now, if this explosion happens in a gas cloud, which is to be expected if these are massive stars or something, so, then what will happen is that the X-rays would ionize the gas out to some radius. The UV photons would hit dust to high temperatures. And in fact, up to a distance of about 10 parsecs, it would hit dust to a sublimation temperature. So when you hit dust to about 3000 degrees Kelvin, it sublimates on a time scale which is shorter than 10 seconds, which is the duration of this event. Now, the sublimated dust emits most of it, you heat up the dust, and it cools down by thermal emission. Most of the energy of the UV that is absorbed by the dust is then converted to infrared radiation.
Sorry, I'm lost. So you have both UV and X-ray. What would X-ray do to dust?
I will talk about it in some detail in a minute.
So it's important that you have both.
It's important. I will say something about it.
But why is this sublimation important? Why can't you just heat the dust and cause the emission?
Oh, it can heat, but the point is that it does sublimate.
It does sublimate.
Up to
Is
10
what you're
parsecs.
saying.
Yeah.
Okay.
It does sublimate the dust up to 10 parsecs.
Oh, that's why it does. That's why the closer dust isn't hotter.
Yeah, it's
Okay.
not hotter. It's the same temperature, but it sublimates much faster.
Right. Okay.
Okay, so all this UV radiation will be converted to infrared emission. In the infrared, I'll show you that we know how to estimate the amount of energy that goes into this UV, which is about 1% of the gamma ray energy that we started with. Now, some point that is sometimes confusing. What would be the duration of the near-infrared emission that we would observe? So the duration will be dominated by the difference in arrival time of photons, let's say, along our line of sight, and photons emerging from an angle which is the opening angle of the jet away from the line of sight. Okay, so the difference in the distance between us from this point to this point is the angle squared, it's cosine theta, right? So it's theta squared times the radius. So the duration is theta squared r over c, okay, which is about 10 days for typical opening angles. Now the thickness of this region, okay, does not contribute to extension of this light pulse, because it's all mediated by photons. So you have a UV photon, if it's absorbed here and emits another infrared photon that continues here, that produces no time delay. The only time delay is with respect to the line of sight. So this will produce about 10 to the 52 Hz per second pulse with a temperature of about 3000 degrees Kelvin. And I'll explain some of the physics now in more detail. This is just to get you the global picture. Now, one comment, this destructive dust flash that is produced by reverse shock is very difficult to observe. It lasts for 10 seconds, about the duration of the GRB. And it's in UV and soft X-rays. And these are observed with narrow field instruments. So typically your instrument is not pointing to the gamma ray detector is a wide field, so it sees the gamma rays. Then you need to point your X-ray or UV telescope to the event. This takes time, and by that time, this is gone. So we don't see this directly, so I'll try to convince you that we know how to estimate the properties of this destructive flux based on what we do observe. You're skeptical, Andre.
Dust, gamma rays, X-rays, too many ingredients.
But you wouldn't, there's no infrared survey that would have just found because you only see the GRBs that are pointing towards us, but these events you should see much more commonly, right?
But
but we don't have anything that looks.
No, but if they do not point at you, they're going to be extremely fainter.
The thermal dust emission will be fainter?
Much fainter, because again, the time scale, if you are looking down the jet here, the time scale is determined by this theta squared r over c. But if you are looking from here, you lose this theta squared factor.
So it's like the same luma, it's the same power, it's the same total amount of energy, but it's spread over a much longer period of time.
Yes.
Got it. Okay.
So you won't be able to see.
I see. Okay.
Yeah. Okay. So okay, to explain how we know how to estimate this near infrared and destruction and so on, and maybe convince Andre a bit that it's all sort of solid. Let's do some of the basic things here. So first,
sorry, can I interrupt? So, why is it rare? That's because you usually do not explode inside the cloud or something?
I'm not saying that it is rare.
So you're saying many...
I think that many of them could be...
But we have not seen this red kilonova-like light curves in the optical afterglows. This is the first one, I understand.
I think that there may have been some other examples. I will show you later.
Okay.
I think that's it. But okay, I will show you some things that are the cloud properties could be different. If the cloud is very thick and it has a very high column depth, it could extinct on the also on the infrared. And there is a large fraction of what they call sort of dark GRBs, which are very heavily extincted. Okay, let's not go into this. Okay, so first a word about the dynamics to understand how what happens here. So the first point I want to explain is that this reversal going backward into the ejecta is mildly relativistic when it crosses the ejecta. This is due to the following reason. So first, when the jet plasma goes into the interstellar medium, its density is much higher than the density of the surrounding medium. So it's like a wall going into the gas. So it pushes the shock wave at the velocity of the piston, at the velocity of the jet, into the ISM. And the reverse shock that goes backward into the ejecta is very weak and cannot decelerate it significantly. Now, as we go in time and this plasma expands, the density drops. And at some point, the reverse shock becomes relativistic. It starts hitting up significantly this plasma and decelerating it significantly. And this happens when the density drops to gamma squared times the interstellar medium density. Now we can calculate at what radius this will happen. To do this, you need also to know the thickness of the shell. The thickness of the shell is determined by its own expansion. So we have some jet with varying Lorentz factor. The difference from c of the velocity is 1 over gamma squared. Okay, so there's a difference in velocity, which is 1 over gamma squared. So the thickness is r over gamma squared. So you put these numbers, you put this thickness and size and so on, and you get the radius when the shock, this reverse shock becomes relativistic. The place that this happens to be when the mass of the surrounding medium is the mass of the jet divided by the Lorentz factor. Okay, and this implies that at this time the jet converted a significant fraction of its energy to heating up the interstellar medium, because the energy of the interstellar medium is gamma squared times the mass of the heated interstellar medium. So if you think when you pass a relativistic shock into a medium, the random motion of the particles behind the shock is the Lorentz factor of the shock. So this is 1 gamma, but then everything moves towards us with another factor of gamma, so this is gamma squared. So the energy of the heated CSM is gamma squared times the mass of the CSM, which is 1 over gamma of the mass of the shock, which is gamma times the mass of the shock c squared, which is the kinetic energy of the jet. Okay, so what happens is that at this deceleration radius, the shock becomes relativistic. Now, since it becomes relativistic and this is the thickness of the shell, it also implies that at this time, this shock crosses through almost all the jet plasma. So at this point, you have roughly half the energy, let's say, in the heated interstellar medium, half of the energy in the heated shocked jet plasma. Okay. And the shock that heated the plasma here was mildly relativistic, Lorentz factor of 1. So the temperature here behind the shock is about a GeV. Okay. This is independent of all the other parameters that you assume. So we know what the temperature is. And finally, once the shock crosses here, there is a very rapid rarefaction that goes into this shocked jet plasma that cools it down and suppresses the emission from the reverse shock. And this happens to be on a timescale of about 10 seconds, which is comparable to the duration of the GRB. Now, this is a coincidence at this point. So this depends on the energy of the explosion and the density and the Lorentz factor. Just happens to be similar to the duration of the GRB. It didn't have to be this way, but this is the way it is. But it does imply that this emission of the flash is on a timescale comparable to the duration of the GRB. Now, what would be the luminosity produced by this reverse shock? Okay, so the forward shock plasma is heated up to a temperature which is gamma times the proton rest mass, because the Lorentz factor of the shock is gamma. The reverse shock plasma was heated up just to the rest mass energy of the shock of the proton, because the shock is mildly relativistic, it's not highly relativistic. So the temperature in the backward shock plasma is gamma times lower than the forward. This implies that the synchrotron emission from this reverse shock plasma is Lorentz factor squared lower frequency than the forward shock. And since the forward shock emits at tens of keV, which we see, this means that the minimum frequency of the backward shock is at EV roughly.
Didn't you assume 1 per cubic centimeter on the previous page? And yet you are talking about clouds.
For this?
Right, isn't it 1 per cubic centimeter?
So first you see that the dependence is very weak. If you go to 100, it doesn't.
But in the cloud it will be like 1,000 or something, no?
Not in the vicinity, and you should probably not in the vicinity of the GRB.
Because it is circum-stellar rather than cloud. Okay. But later you will assume higher density, no?
No.
Not really?
No. I show you the dependence on the dependence.
Okay.
It's very weak.
Then why did you talk about molecular clouds?
Because
Because you want to have
I
dust.
want dust. And massive stars often explode near dust.
Okay.
Okay, so the forward shock emits at about tens of keV, the reverse shock at EV and up. Now, what would be the flux? These collision shocks accelerate particles, electrons, so that they have equal energy per logarithmic energy beam, roughly. Now, if the electrons lose all their energy, there would be equal luminosity in equal frequency, logarithmic frequency beams. Now, so if the electrons cool fast, they lose all their energy to synchrotron radiation, we would have a flat spectrum equal luminosity in photons with equal logarithmic frequency beams. And the reverse shock luminosity would be similar to the forward shock luminosity because they have the same energy. Now, at the reverse shock, which has lower energy electrons, okay, which emit at 1 electron volts, these electrons probably do not lose all their energy to radiation. The cooling frequency, the frequency at which electrons radiate that lose all their energy on the dynamical timescale is about keV. This is also we know from the forward shock. So in the backward shock, Lorentz factor, if you take a frequency which is 1,000 times smaller, Lorentz factor which is 30 times smaller, the cooling time would be 30 times bigger. So only some fraction of the frequency of the electrons would be, of the energy of the electrons would be lost in the reverse shock, and this is going to be about 1/30 of the energy that is being lost by the keV photons, the high energy photons that we lose. So if we take this factor, we get this estimate of 10 to the 49 ergs per second for the optical UV emission of the photons and the reverse shock. Okay. So we use just the scalings with the simple dynamics that I've shown you with the observations of the forward shock to get these numbers. Now, we said that observing this flash is difficult because you have now field instruments that usually do not point to your GRB, but in some cases you do have rapid observations on shorter than 100-second timescales. And as you can see here, okay, this is some light curves of X-rays and optical UV emission. This is U-band, so UV emission. And there's this group here, all these blue ones, they have luminosities larger than 10 to the 49 ergs per second on this tens of second timescale. And they're very rapidly falling.
And those curves have nothing to do whatsoever with the late time optical afterglow.
Right.
They will be like well above.
Yeah, they decay very fast and then they. So this strong optical UV emission is not uncommon. There is one case where there's a claim for directly observing dust destruction by observing the extinction reduced over these tens of second timescales. Okay. This is a very difficult observation to do, so we don't have many of these. And as I've mentioned, there are several cases where prolonged infrared, near infrared emission has been observed. And it could be, I believe, due to this dust emission. Now, so we know we have this flash. What does it do to dust? And what do different photon energies do to the dust? So let's start with the 1 to 7.5 electron volt photons. So these optical UV photons, typically the size of a dust grain is a fraction of a micron. So these are photons with wavelengths shorter than the dust size. So the cross-section for absorption by dust is approximately the geometrical cross-section of the dust. So all the UV photon luminosity that hits the dust is absorbed and heats it up. Now the heating is balanced by thermal radiation and sublimation. Okay, so this sets the temperature equilibrium. Now because the sublimation rate is exponentially dependent on temperature, it is just the probability of a molecule having sufficient energy to escape the grain. The temperature at which you get sublimation on 10 time seconds is not sensitive to the grain size, or the composition, and duration of the pass, and so on. It depends mainly on the binding energy, and it ranges between 23 and 2700 Kelvin for different types of grain material, graphite. Now, at these temperatures, the cooling of the grain is dominated by radiation. The cooling becomes dominated by sublimation at higher temperatures.
So for you, sublimation is not the mechanism of destroying the dust, but rather just cooling the dust.
No, sublimation is ejecting.
I understand, but you are interested in sublimation to destroy the dust or to cool it. So if you shine UV on a dust particle,
yeah,
it will emit infrared photons and it will also sublimate. Both of this infrared photon emission and sublimation are a cooling mechanism.
Right.
So are you interested in sublimation as a way of cooling it or as a way of getting rid of the dust?
No, I'm not interested. This is the way it is. Now, I'm saying that because the sublimation temperature is below this 2800 Kelvin, most of the energy that will be lost will be to infrared radiation.
He's saying he can set an equilibrium only accounting for radiative cooling. He doesn't have to account for the sublimation cooling when he does.
Then why does he mention sublimation if it does nothing?
Well, if you go very close to the burst, when the luminosity is much higher, then you would reach temperatures higher than this, and cooling would be dominated by sublimation.
So
only a small fraction of the radiation.
Also, this is the explanation for why we see 27 and below infrared emission, because at higher temperatures it will be sublimation.
That's right.
Correct?
Yeah. And as you go to farther away distances, the maximum distance out to which you sublimate the dust is like 5 parsecs for typical parameter. At that distance, the temperature is going to be this, and most of the energy will be converted to infrared radiation. At smaller distances, most of it will be converted to sublimation.
So you should never see infrared at whatever. It's not longer infrared, perhaps at 3000 Kelvin.
Yes, you should see.
That's the prediction.
That's a prediction. Yes. Okay. Why did I talk about up to 7.5 electron volts? So let's take higher energy photons, 7.5 to 100 or so. So between 7.5 and the hydrogen ionization energy, most of the photons are absorbed by excitations of molecular hydrogen, which is abundant in the cloud. And as we go above 13.6, most of the energy is going to be absorbed by ionization of hydrogen. So not much will be left for heating the grains. Okay? Unless the energy carried by these photons is large enough to completely ionize the cloud. And then you ionize the cloud, and then the radiation hits the dust. And the maximum mass of the cloud is about 10 to the 4 solar masses for this to happen. And if this happens, then these photons would increase the sublimation luminosity by a factor of 2 to 3. And finally, what about 100 eV photons and above? So these photons are attenuated mainly by ionizing metals, so everything that is beyond helium, mainly CNO and some silicon and sulfur. So the optical depth of a cloud for ionization by these X-ray photons depends very strongly on the energy, because the ionization cross-section drops like the energy cube. So for a cloud of 10 to the 22 per centimeter squared column density of hydrogen, which is a typical cloud, the optical depth for kV photon is about 1. So if we go to 10 kV photons and above, they do not deposit almost any energy in the cloud. That's why we see the reason. In addition, when such a high energy photon ionizes CaO, silicon, in a grain, the secondary electron carries about 1 kV. And at 1 kV, the secondary electron escapes the grain without depositing its energy in the grain, so it doesn't hit the grain. So what they do is they charge the dust. They do not hit it, they charge it. Okay. Now what about KV photons? So the KV photons, they carry typically 10 times more energy than the UV photons, because, as I mentioned, these are produced by electrons that lose all their energy radiation, while the 10 eV photons produced by electrons, it was only like 10% of the range. Okay, so they carry 10 times more energy. So you would think that maybe they would, and the secondary electrons produced by keV photons, the energy of those are less than keV, and they do deposit all their energy in the grain, so they would heat up the grains. But the cross-section of the grain for absorption of a keV photon is about 0.1, because the ionization cross-section typically is at -19 for these atoms and so on. So only like 10% of the X-ray luminosity that goes through the grains would be used to heating them up. Okay. So at most, the luminosity of the X-rays is giving you a similar contribution to the luminosity of the non-ionized photons. Now, in addition, most of the ionization in a cloud happens in the gas phase. So most of the energy loss is to ionizing the gas, not to heating the grains. So again, this will not give you any significant addition to the destruction luminosity or sublimation luminosity unless, again, you have enough energy in the X-rays to ionize the metals in the gas. Then you ionize the metals in the gas, and the X-rays hit the KV X-rays hit the grain, and this would add some similar contribution to the grain heat. Okay, so overall, we have 10 to the 49 ergs per second times 2 or 3, depending on the situation in the cloud, with respect to these high energy photons. Now, one last comment about the physics of this. The charging of the grains by the 10 keV photons is important, because you can charge the grain and produce such an electric field that would lead to grain fission. And this is actually what's going to happen in this grains. So it's more difficult to lead to fission of smaller grains. And if we take the X-ray, typical X-ray luminosity, 10 keV photon luminosity, and we take 0.1 micron grains, you see that they can lead to fission of grains out to a distance comparable to the dust sublimation distance. So what will this do? When we break up the grains, okay, we start breaking them up, they get to some small size, this 0.1 micron, they would not break below that. Since if you take infrared photons, the wavelength of the photons is much larger than the size of the grain, so this does not change the absorption of infrared photons. But for UV photons, the wavelength of which is comparable to the grain size, it would increase the extinction. Okay, so you get higher absorption of the UV photons. Okay, I mentioned all this first because it's interesting physics, but also there were all sorts of erroneous claims in the literature about all these things.
But the moral of all this complicated stuff is that these dusty clouds like to emit infrared and nothing else.
Yes.
Right? In a simplified fashion. So
yes.
Right?
Yes. And we know what the luminosity would be roughly and what the duration would be and so on. Okay, so now we go back to this event that we've seen and we take its parameters, and now we don't know what the exact distance is. Okay, so I give all the numbers here normalized to some 2 gigaparsec distance, and okay, you can change this distance and see how your conclusions are modified. So if we take a characteristic 2 gigaparsec distance, the energy of the gamma rays is a few times 10 to the 53 ergs. The destruction or the sublimation luminosity is going to be a few times 10 to the 49 ergs. Sublimation distance of 10 parsecs. Dust luminosity of 2 times 10 to the 42 ergs per second, and dust temperature, okay, of the sublimation temperature that will give you a peak at 1.7 microns. You can compare this to the observations. The dust luminosity compared to the K-band luminosity, okay, it's about 1, and with some not very strong, but some dependence on the distance. And the temperature is about, as we said, something like 2700 Kelvin, depending a bit on the grain properties. The flux, the ratio that was observed corresponds to 2400 Kelvins. Yes.
The E gamma that you have there is isotropic gamma?
Yeah, everything is isotropic equivalent. Okay. We don't care because everything is within the beam of the jet. We don't care if it's a sphere or a beam. We do care about one thing, which I'll mention in a second. Okay, so this dust sublimation explanation is valid as long as the distance is not, the redshift is not larger than about 1. There you cannot get this high infrared luminosity that you observe. Now, the duration of the burst, we said, is this theta squared times the sublimation distance divided by c. And the infrared emission lasts for I don't know, more than 8 days. So we have a lower limit to the opening angle from this, which is 0.04 radians. And there has been a break in the X-ray emission of this burst that is interpreted as, now it comes to the question of whether it's collimated or not. So as the jet decelerates and its Lorentz factor decreases below 1 over its opening angle, it starts expanding and the luminosity drops faster. And this break had been observed in the X-rays, and it was interpreted as an opening angle of about 0.05. Okay. So this is all consistent and makes sense.
Can a normal kilonova last 90 days? Because you are saying, like the time scale, is it because you said kilonova is fast and whatever?
No, it shouldn't last 90 days, but this is an upper limit. We didn't see it for 90 days.
No, I mean to argue that this is not a kilonova, but rather a long GRB. Can you use the time scales of the infrared emission, or is it somehow irrelevant?
It's sort of, if we had observations longer times, we could have said something. We don't have this information. We've seen something at days, then there was a later, much later measurement at much longer time, only an upper limit. So
oh, it's only upper limits at later times.
Yes.
Okay.
Okay, and the gas cloud properties that would be required for producing this are typical gas cloud properties. A 10 parsec cloud with a column density of 20 to the 22 per centimeter squared. It's what's typically characterized. And if we want all the ionizing photons to contribute to, the mass should be about less than 10 to the 4 solar masses. These are all typical cloud properties. Now, if we put this gamma burst in the cloud in not a special position, okay, the optical depth of the cloud is before the sublimation and ionization is about 4 or 5, we expect a residual optical depth of about unity. Otherwise, we need to put it just at the edge or something like this. So we do expect a residual optical depth of 1, and we do have evidence for this. So comparing the X-ray and the optical UV fluxes, there is a lower limit to the extinction of UV photons, taking into account the fact that if you have synchrotron emission at low energies, the synchrotron flux will not drop faster than mu to the 4 thirds. Okay, so this is this mu to the 4 thirds, and there is this suppression. It was identified by these X-ray observations. They dismiss this as an explanation for the suppression of the UV. They say that there should be some other unknown source of absorption. Okay. Why do they dismiss it? They say because it's not consistent with the later afterglow observations. But we just mentioned that the later afterglow observations are extremely red. They are so red that you invoke a kilonova to explain them. So certainly you cannot say that there's no extinction there. Now, the typical column density, okay, that would be required for this tau v, which is about 5 times 10 to the 21 per square centimeter, is higher than the column density inferred by the soft X-ray spectrum. So the soft X-rays are absorbed by the cloud 2 by ionization, and the measured value that they obtain from the soft X-ray spectrum is about 1. So, and this ratio sort of is a typical, an optical depth of 2 for visual, and the column density of 10 to the 21 per square centimeter from the gas is atypical. It's not typical to the clouds in the galaxy. But, well, 2 things should be mentioned. First of all, the dust the metal content of the gas phase in the dust in the cloud and the ratio to the dust content of the cloud at high redshifts would be different than here. And also, I say that this increased ratio may be a characteristic signature of this dust sublimation. Why? Because the X-ray photons, we said, they ionize the metals in the gas cloud. So they reduce the photoionization optical depth to values which are lower than would be for the same column density. So you would infer a lower NH column density based on the X-ray flux. And on the other hand, the sublimation, the fission of grains increases the UV absorption. So this low ratio of optical depth in the visual to column density in terms of the X-rays is a signature of such a process. Okay. Last point, the galaxies. Okay. Let me swap out for this. Good. So this is the picture of the. This is where the burst was localized, and there are several galaxies here, A, B, C, D. The proponents of the kilonova model associate the burst with this galaxy A. This is a relatively low redshift galaxy, 0.08. Okay. The chance probability is not, the chance association probability is not low, as you can already see from this picture, but this could be the galaxy. This would imply a very low luminosity for this GRB, so atypical of cosmological GRB, long duration GRB. Now, we argue that there could be a different association. This galaxy B has a spectroscopic redshift of 0.47, and these two C and D have a photometric redshift of 0.5. So there appears to be some group here. Now, there is no galaxy at the location of the burst, and the upper limit on this, on its luminosity, is about corresponds to about 1% of an L-star galaxy at this redshift. Now, this is not unreasonable, because about 10% of long-duration GRBs originate from such dwarf galaxies, and these dwarf galaxies usually are found near more bigger massive galaxies, and this could be just a dwarf galaxy related to this cluster of galaxies, the group of galaxies 0 at redshift 0.5. And if this is the correct redshift, then the luminosity of the GRB is the usual 10 to the 53 ergs in gamma rays. So we argue that this is an alternative, and this galaxy might be detectable if you observe it with HST or JWST for long enough. You could detect this dwarf galaxy, and this would prove our suggested alternative explanation.
But isn't it obvious that it is closer to the bigger one?
Yeah, it is closer. The distance here is like 50 kiloparsecs, which is yeah, it's closer to this one. But 50 kiloparsecs is a typical distance for a dwarf galaxy.
It's basically the SMC.
Yeah.
And it comes with a prediction. Point a good telescope, you will see a galaxy.
Yeah.
Correct?
Okay, so this is the story of
Will you send
Wait,
us?
can you go back?
Yeah.
So there is HST imaging already.
There's an upper limit. Yeah, this is where this
Down to
point-
28. Okay.
But what can you? How can you see it if Hubble cannot see it?
Hitter exposure. This is an existing detector. Right? It's not a.
I mean, in principle, you could go a couple magnitudes
You could
fainter.
go. I can still argue that it is still fainter galaxy.
Yeah,
I would start feeling uncomfortable.
Okay.
Okay. So I will not bore you with the details of the afterglow. So we're almost out of time. So let me just summarize. If you want to ask me about the afterglow, related to that. So what the main messages? First, extended 10-day strong near-infrared 10 to the 42 ergs per second thermal emission at 1 micron is sort of an expected phenomena following long duration GRBs. If they are reside near or within molecular clouds, this should happen. As I've told you, we have some examples where maybe this has been observed, and I think that this is a good candidate. The ionization of metals in the cloud and the fission of grains in the cloud would lead to high ratio of tau V to NH inferred from X-rays, and this is another signature of this thing, which has been observed in this particular case. Now, if we talk about the particular event of this 21, 12, 11, I think all its properties are consistent with this interpretation. The luminosity is consistent, the temperature is consistent, the duration is consistent. The cloud properties are just typical cloud properties. There's nothing special about any of the parameters here. It's exactly what should happen. We have, if our explanation is correct, we expect this burst to be associated with a dwarf galaxy at a redshift of about 0.5. There is a group of galaxies there at that redshift. The distances are reasonable. And in principle, with deep HST or JWST observations, you could identify this dwarf.
What if the dwarf is behind that A galaxy? From there, would one be able to see it still? Because it's pretty close, right? So it's probably there.
But that's different redshift, I think.
Yeah, but so
You're worried about
yes.
the extension of that's a good. I didn't check this. That's a good question because it's difficult to say from the contrast here what the contamination in this location is.
Right.
Okay, so maybe I would have another way out. But it's better that they detected the galaxy.
Yeah.
Putting this at this redshift of 0.5 makes this burst a regular long duration GRB, not anomalously faint long duration GRB. So it's another point in favor of this explanation. So I think we have an alternative to the Neutron Star merger explanation. You asked, okay, if we don't see a supernova and it's not a Neutron Star merger, what could it be? So first of all, if it's at redshift 0.5, there could be a supernova, yeah? In addition, as we said, there are several, at least a few, the same number of, even larger, bright, luminous cosmological GRBs that are associated with supernova. We have a similar number of such GRBs that have very strong stringent upper limits in the presence of the supernova. So,
Which you explain out by extinction, or what?
So it could be extinction. But in those cases, in a few cases, it's probably not extinction because we measure the afterglow. So it could be a different progenitor altogether, which probably is correct. So if you want a collapse of a failed supernova, a collapse of a massive star to a compact object followed by accretion, could produce this GRB without this ejecta. This could be so, but this could be either a supernova which is a bit faint and not observed because it's redshift of half, or another type of explanation. But you don't need the Neutron Star merger if you have this dust explanation.
Do we have more questions? Andre has a question.
You show strong bias against me.
No, you just had a lot already. I thought.
So, how to say, is yes, sorry, I have to think more about how to formulate this thing, sorry.
There's 2 more days.
I certainly don't know much about this field, but there's one thing I would like to ask. Couldn't some of this be experimental work that could be checked, the evaporation of dust particles, the gamma rays, etc.? Is there any has any work been done in that regard, experimental work on the Earth in laboratories?
In the laboratory. I'm not sure actually.
What?
How do we know these sublimation temperatures?
Yeah, sublimation. I mean, can you do this experiment at the lab in?
Yeah, that is measured. Yeah,
That's been done.
that's been measured. Yeah, the energy required for
On Earth.
on a silicate or a graphite is well measured. It's not a theoretical calculation.
Yeah.
But the grains in the interstellar medium could be different than the species of silicate that you have in the lab. It could be amorphous, and they could have different compositions than what we suspect. So this can change a bit the energies. But for silicates and graphites, this is well measured, and these are the numbers that we recognize.
So those people who said that it is a kilonova.
Don't hold it against them.
Huh?
There's a
Did you talk to the people who said that it is a kilonova or whatever?
Yeah.
And so what is like current status of this debate?
Well, I don't know.
Do they have some arguments against your, like, is it really so difficult to distinguish the two things, because they seem by description to be very, very, very different in their original energetics and whatever. So how come?
No, they're not very different. The luminosity of a kilonova is typically 10 to the 42 ergs per second.
No, but in terms of the total, like in gamma ray bursts, for example, right? The kilonova is not expected to produce 10-second duration gamma ray burst or something, right?
Right. You have you have to have something else producing the gamma rays. It's nothing to do with the kilonova. You have to have a jet.
But how can it be that you have simultaneously a kilonova and a long duration? How can they interpret this thing as a kilonova if they had a long GRB?
This is a challenge. Having a 100-second thing coming out of a Neutron Star merger is a challenge. There is no good explanation of how this happens.
So it would be a very strange kilonova indeed, which produced a long-lasting gamma ray emission, correct?
Yes, but as you, as one of them said, well, you can extend the 0.2 seconds to 1 second in some cases. 1 second to 10, and then 10 to 100, and fine.
But what about this GW event, which is canonical kilonova? Did that produce long-lasting GRB?
So it produced, as I mentioned, a gamma ray flash about 2 seconds.
2 seconds.
For much lower luminosity, of course.
And also much lower luminosity.
Yeah, 6 orders of magnitude less. Could be.
Andrew had a question.
Okay, Marcus. As I understand it, there's not like a clear sort of separation between short and long.
Yeah.
GRBs, like some of them.
Certainly there's an overlap, it's not distinct.
So I guess what causes people to invoke the kilonova or the short GRB?
In this case?
Yeah.
Well, it's this infrared emission that I'm sure. This is everything that we had is this few points in the infrared.
Does it look anything like GW?
So, okay, my view is that it's very difficult to say because you do have a regular afterglow there. So you need to take this observed fluxes, subtract the afterglow, and then see what you're left with. And this subtraction is very model dependent. So to say that it's similar or not is very difficult. The one thing that we know is that this flux ratio of infrared to, let's say, 1 to 2 micron is very different than 17/870.
Oh, then canonical kilonova.
There's one canonical kilonova. You have a question?
Just quick, I wanted to see the afterglow slide. If you
You want to see the afterglow slide? It's his fault. So, in order to interpret this as a kilonova, you need to subtract this afterglow. Okay, we see the X-ray afterglow. This is certainly produced by the forward shock going into the interstellar medium and so on. And then you have to use some model to say what would be the optical UV infrared emission from this shock. And this is highly model dependent. Just show here. So the afterglow model depends on many parameters: the energy of the explosion, the Lorentz factor, the opening angle, the fraction of energy converted in collision as shocks to electrons and magnetic fields, the number density, the spectrum of the accelerated electrons, the extinction, and so on. And many of these parameters can vary by orders of magnitude. Now, the models that describe the afterglows are extremely simplified. You take a top hat jet, uniform density, constant values of epsilon E and epsilon B, and so on and so forth, and then you get something. But in principle, I would expect strong deviations from this simple picture, because all of these parameters could vary, and we don't know what the structure of the jet is, we don't know the structure of the CSM is, and so on. So I would say deviations from the canonical picture should be the rule, not the exception. And it's very difficult to actually constrain because of all these, because of this very large number of parameters. It's essentially very difficult to constrain the parameters of the model based on observations. For example, the fit that is shown here on this plot to the afterglow, the uncertainty in the inferred energy is 2 orders of magnitude, and the fraction of energy in magnetic field 4 orders of magnitude, and the density 3 orders of magnitude. So I mean, you cannot really use an afterglow model to say, okay, this is the prediction of the optical UV infrared, and you can subtract it and get the rest. You can get whatever you want. That's what I want to say.
but using the standard prescriptions, do people get reasonable subtractions?
Why? But you need some. What do you mean? Okay. The break here is achromatic. It's chromatic. It's not achromatic.
Oh, it's chromatic.
It's probably chromatic, so it doesn't fit the model. Yeah, so I don't want to go into all the detail, I guess.
But didn't this canonical kilonova also have this afterglow things?
The X-rays and value.
Like, cannot you just compare the pictures of this kilonova and the only canonical one in existence?
No, but you need to subtract the afterglow.
Did not the canonical kilonova have afterglow?
No.
Oh, it did not. So it was pure, supposedly it was pure radioactive
Yeah,
thing.
it seems that the density in that case was 10 to the minus 3. It exploded in a sort of elliptical galaxy with very low.
And today we
density.
understand
Therefore,
that
there's very little. So we do see radio and X-rays, and then we might have seen some part of the optical afterglow, like 100 days after the decay of the kilonova. But we don't have we cannot compare these two.
but that kilonova was clearly radioactive, you are saying.
Kilonova was fully radioactive. It would not fit this picture. For this picture, you need to add the afterglow in a dense medium.
Right.
Thanks.
Another question.
Do you have a spectrum
Of the
of like this event?
you mean in the
Like what was a spectrum?
in optical in UV or which
Just like any. I was just thinking that there
the-
might be like signatures from the kilonova versus like.
so
emission from dust.
we don't have an infrared spectrum of this. It was barely detectable, in the K band. It's very difficult. This the luminosity. If it's the luminosity that range of traffic is very difficult. It's challenging to detect and certainly to take infrared spectrum. We have X-rays, not in this. This could have been differentiated.
So thank Kelly again. And you're around at least through Thursday, right?
Yes.
We're going to dinner tonight, I think with you two.
I can go too.
If you want to get, yes, that would be great.
All right.
But I can only do 6:30. Is it okay, Ali? 6:30? Because I teach a class from 5 to 6:15. Or you can go with these two guys earlier.
Dinner? No, I
Dinner.
thought that dinner should be later. No?
Okay.
6:30.
Seems like he's okay with 6:30. That's great, thanks. Thank you.
Yeah, good. Ellie, have you met Marcus?
Yes.
Okay, good.
And took care of me.
Hey.
Hi.
Nicole told me that there's something going on in your Inspires account. I guess what you put on the pinning things is not reflected on your Inspires or something like that.
Who said that?
Nicole. She didn't. I don't think she.
Oh, tell her to just send. You know, I didn't want to make that. It was a huge pain. Tell her to just. Usually Carol Ann would make the.
So this was a perfect example of everything that is wrong with astrophysics, right? Because you whatever build up your theories, whatever, then somebody comes and says, "Oh, it's all dust."
Yeah. No. Yeah.
And he could be just right.
No. But but he did it first. That's the key. He's not saying after the fact that it's dust. You made that prediction in '99, right?
Yeah. 2000.
So
No, I understand, but
he was thinking you made it up after the.
No, I wasn't thinking. I'm saying that this is the thing which is wrong with astrophysics, right? Because people do elaborate theories, whatever, then somebody comes and says you have forgotten about the dust, and it turns out some stupid dust is the main defining factor of this whole. No, but really, right? I mean, I think I'm quite serious. I think a lot of things in this thing is to include. It's like I think Marcus asked me what's a good textbook on plasma physics, and I searched through them, and the best one is by Kadomtsev, which unfortunately is not translated into English. And he starts the book by saying the main problem in plasma physics is that there are so many processes going on simultaneously that one need to single out the one which defines the. No, but seriously, right? I mean, dust, right?
Astrophysics is a mess.
Astrophysics is a mess, exactly.
Dust.
In many cases, it is a mess, right? And identifying which concrete messy process is.
So Martin Rees said that, particle physics is like chess, and astrophysics is like mud wrestling.
That's good.
The paper you presented, that Jeff Ryan was on that paper, right? I think I just remembered.
Yeah.
Yes, the paper Jeff was on.
was.
Okay.
Yeah. Jeff was here as a grad student. Yeah. So, but I'm not sure. Yeah. I mean, I think he just did afterglow modeling. So yeah, he has this thing called afterglow pi. So, but it's a chromatic break. Yeah. Okay. Because Austin, who was just here, modeled 170817 with just synchrotron emission to get, because the X-ray and after that radio are still visible. Like,
yeah, still visible. Like maybe maybe it would be rising. I don't know.
Yeah, exactly. Yeah, and it seems to be right. So
well, sort of.
Yeah, could that be? That can't be dust though, because that's
no, it's not dust.
So in that case, it's got to be synchrotron.
That's synchrotron all the way. Yeah.
Okay. So
and we know
and we know it was a
the
neutron
density
star
is
merger.
extremely low.
It's very light. 10 to the
Extremely,
minus 3.
extremely
Yeah,
low.
that's right.
You don't have. It's not a molecular cloud.
Yeah, that's true. Sure. Oh, I see. Okay. So I like your model. I think so. Yeah, makes sense because maybe it's too far away, but in some cases they have X-ray observations. But I think it's too far. Or of the host galaxy, where they can estimate the X-ray. Sorry, the density.
The density.
Yeah.
So there are these. They used to be called dark GRBs.
Yeah. No, I remember.
Then,
yeah. Host. Yeah.
But then they are when there was the survey. I think it's Panama or something. So when they did rapid follow-ups, and they've detected very high column densities, different from the X-rays and the optical UV with very large extinction.
Yeah.
Optical depths of 4 or 5.
Yeah, it makes sense if they're
so which would have been characterized as dark. but they did find emission and they did find very strong absorption. So I think that this is a common thing.
Right.
Sure. It's not a rare thing. So sometimes.
Yeah, another thing is it's insane to have a long, short GRB. Like neutron star mergers, like you were saying, 0.1 seconds, maybe. That's even stretching.
That's even stretching. Yeah.
So going to 10 is crazy. But yeah, interesting. Except there are these extended emission short GRBs
I was just gonna mention
that are like 60 seconds or something. So that's probably something else, but yeah.
So this one is not
Extended.
of this
Right.
A short extended is short at the beginning and then extended. This is long in the beginning.
Yeah, exactly.
This is
Okay,
a few
so
seconds.
so
then it has another.
Right.
Yeah, and also if you look at the hardness ratio, it's just a regular.
Oh, okay. So it's not.
GRB.
Okay, so it's soft.
It's soft.
It's
So it
soft,
just sits in the middle of this
the
hardness ratio and duration just now. And I don't know. So they were claiming that the Amati relation, that this one falls on the short GRB ratio.
Oh.
But this depends on the distance.
Oh, right. That would be at the point
If
0.08.
it's 0.08, it will be there. But if it's 0.5, it's just on the long duration GRB relation.
I see.
So
Okay, cool. So
this is not a short GRB. I mean,
right. Yeah, the sun's much more reasonable. What can you do to? JWST. Can you do a proposal?
I know.
No, but with Avishai or someone.
Maybe one of them will do it. Yes.
Yeah. No, but that'd be a good. That's a nice.
Shy on maybe some of them.
Yeah, that'd be a really good thing to look at.
Yeah, I think so.
Nice.
You have a clear prediction.
Yeah, it's there or not. Yeah, that'd be really cool to see because the angular resolution of that error circle is if you see a galaxy there for sure.
Yeah.
Right. That's like sub whatever arc second-ish. Yeah. Nice. Cool. So I'm gonna come. I'm also gonna meet you Thursday morning, and I'll be at your colloquium, of course.
Yes.
I'm teaching tomorrow, so I'm kind of busy.
Good.
But I'll come to dinner tonight if I can. Is there?
I'm really happy to.
Yeah. Okay.
So Thursday morning, you want to chat?
Yeah, if you want to, and if Marcus, I have I'm flexible, by the way.
Okay. Do we have something marked?
I marked 11 to 12.
Okay.
But if
you didn't tell me, but okay.
Okay, it's on the.
So I'll put it on my card.
Yeah, put it on 11. Can you make 11 on Thursday?
I believe so. Yeah.
Okay, no, it's important.
Pretty sure. Yeah.
Well, when you say you find out for sure, because then I can switch it. Because whatever, or you can.
Is there a place where I can see this? So
yeah, it's supposed to be.
If I don't know about your.
Yeah, there should be a Google Doc that you don't have access to.
You should have gotten. Yeah. I'll forward it to you.
Forward it to me.
Yeah. Okay, I'll forward it to you. Okay, cool.
Thursday I should be good. Yeah.
Okay.
I mean, I'll definitely be here, but for some reason I feel like I'm supposed to be somewhere, but I don't think I am because it's Thursday.
Okay, that's okay because it's pretty flexible. All right, I'll forward that to you. And then I've got something I need to do now, but I'll meet you at dinner. So that's is it 6:30?
6:30.
Okay, perfect. Excellent.
And then do you have any dietary restrictions or anything like that?
Has to be tasty.
Okay. Okay, sounds good.
All right.
I'll think carefully and then
Okay.
I'll send you an email once I have all the details and reservations ready.
I'm here.
Oh yeah, okay.
I'm here. I'm not going anywhere. Okay. So we'll chat Thursday.
Yeah. And we could. Yeah, I have a few minutes now if you do.
Sure.
Okay. Yeah.
You want to get some?
Get a coffee. Well, welcome. I just saw you. Yes, exactly. Oh, you missed it. That's right. Oh, okay, good.
Giờ có thông tin about the
Nobody's talked to me. I just got an email about it.
Roger mentioned that higher wave is a flow.
Right.
And I think that because we concerned about the field 10 times, this time MIO will take that. So we get rather a much better. But of course, MIO so profanity, money, they know how many things you bring. Never Hollywood is it. You saw some job I know so you saw me job, don't bring your lot. So whenever we bring it, that's the idea. Then they know who bring how many things. We still pay, we still demand. Whatever, anything, car, the fair, by my I want to play. But it is a very kind of we have a good chance to take it off. But if we don't do that, we can keep the printer as long as
Replacing that printer with repairable newer printer would be $5,000.
Maybe not that maybe like a maybe more than that.
Well, yeah, we wouldn't get that. We got that one in, I don't know when.
Yeah, I believe but the problem is they don't know what.
So what? How does the how does it work as the like so if an undergraduate working with us and needs to print something out, what happens?
I guess I'm not really know the detail of how I can order. But it is a broad document that you have but I don't know, maybe there's some.
Yeah, no, that's not what people need though, right? You need to be able to say, certainly the graduate students, but and definitely postdocs. But even to undergraduates, like they need a place where it's like, oh yeah, there's some papers, find them, and print them out yourself, right? Like,
yeah, I believe this portable.
I mean, not everybody prints stuff out anymore, right? So it's not it's not that everybody will do that, but does seem like we should find out precisely what the policy is.
So I just let you know earlier in case you go talk to your so they will prepare for the kind of what type of even if you email.
Well, we got an email about this.
That is the internet for the temporal.
Yeah.
This outward document but yeah, we actually want to balance our maybe half 4 years, 4 years later, I don't know. Maybe it's just a fact for a while. But if it's broken, probably not one of the one bad yours. This is a chance.
Yeah.
But as I know, you do this part of the one with the new one, some means getting there. It's fine, but it's because they want to grow. They don't want to waste the money. They want to wait for how many pages. But what is it? Email, how many pages, how many
I mean, the things I worry about are like, I don't know. I worry that it's like, oh, this is like some LaTeX produced PDF that's slightly out of, like slightly, sometimes you get these files which are like kind of the bad PDF, and then like I'm a little worried that it's
grammar compatible. Right?
Yeah,
maybe it's not that good.
Yeah, I don't trust NYU to have tested any of that stuff, right? So maybe it's fine. It's probably not, but it all makes me very nervous.
Well, actually,
I'm not so nervous that I want. I mean, if we wanted to, this is another specific question, which is if we wanted to, and we had $3,000, like let's say I had $3,000.
Nobody can block out this thing. As long as it's working, they put a new one there. That, of course, I don't know whether it's going to work. No, everything stable, phone, everything.
That's all paid by the department, right?
But if we keep the printer there, nobody can take it off. If they use it for a while, but I don't think we use it long enough to give it all the things.
Yeah. But I mean, let's say we did want to buy a new one, would NYU even let us?
I don't know. This is a question because
if they won't let us do it, then
they for now they already don't want to do it. So or whatever. They want to go out. Somehow they didn't say go out. They didn't. But who knows? Maybe a year later. I have no idea. I got the idea.
I mean, this is a typical NYU rollout, right? Because it should have been like if they want to make this. When is this change going to happen?
Temporal is February 17th.
Yeah. I would have expected. I mean, has Raj known about this from us?
No, he doesn't know.
Yeah, I mean, this is the type of thing I would have expected that Raj would have known about in September, right? And
maybe both knows, or maybe he knows how to move in earlier than us.
Right. But I mean, Raj is the person who needs to know, right? Because like, there's many things to consider. You might want to test out.
Yeah.
Like, is there some like sample printers that like, I mean, not for people like me to test out, but like your sysadmin to be like, oh, okay, yeah, that works. I see how it works, and maybe here are the problems that our people would have. Right? Like that would be the rollout I would expect from an IT. But this just seems like we're doing this thing.
But they not. If you say I don't want it right now, definitely about it. Didn't enjoy that.
But it's just like an opportunity now because the department sure as heck isn't going to give us money to replace that. It would be CCP money we would have to spend. I mean, probably we should do it. And the question is like, what's the window? Like, because if there's an opportunity to test to just like test what they install on the 10th floor in a couple weeks and say, oh yeah,
I told you, right? In any case, we will start with our.
The primer is still
Kind
kind of a big deal.
Yeah. So if they start implementing it, because you open the standard with that, the basic is there, so it will block the one way. I said no, that's bad idea. Then someone I said no, okay, block it one way. No, don't block it.
No, you're probably not allowed to.
Yeah, probably illegal. So in that case, and they also contact you for how do you install it. Right now it's the station, so we need some sort of cabinet. So you need to remove the code. You need a small cabinet there, put the big one in there. Right? I don't know how to go, what can do. Oh, you buy a lot of version just uninstall. The small version, so MRU is going to be a lot. Scanner, fax, color printer, everything.
And there's one model.
One model, MRU model, but I don't know whether they give different model, but at least for now I can see it's very large machine. Very good machine. The idea is not bad because,
Having a scanner on this would be nice.
it's nice, yeah, with color printer. But at least as I say, if you want to keep the printer right now, you can use them, you can, but I have a new printer there. So if you want to use that printer, you want to color print, you can use your car or whatever, I don't know. That don't have to have it. But in any case, this is cloud print. Your software is fine, you can do that. You submit the job, software is correct, then you any of them.
And I presume that if I'm on the NYU
anywhere.
Well, what if I'm on my laptop? Like
Any machine, I guess, as long as you install the software.
They have the Linux version of this.
Yeah, I'm not so sure. That's wrong. That is, you can install the software on your computer. I don't know what your machine is for. If your machine is okay, then you can just talk to the button or whatever. So they will pick up from the cloud. Yeah, they know how many pages you print, everything monitor.
Yeah, I mean that's fine. It's all NYU, like whatever. Like
Yeah,
print on NYU systems.
Yeah.
Yeah.
And this is not a. I would say it's not so bad. You later, and when you still along, we have a signal option. So it's not a so bad idea. Maybe.
Yeah, I think that's right.
Right.
Yeah.
But we do use this opportunity after change the data, make that focus further. Not just one zero or a lot. People data there. There's more there.
Yeah, I mean, it takes some carpentry, I think. Right? Somebody, because you have to like basically make a space in that.
I don't know, what I talk to you, I guess you have to think about it earlier, make sure you know what the question, and I'm just prepare for that.
Okay.
And maybe this option.
Well, I'll probably just email them now and update this thing. Thanks.